Hello, and welcome to this lesson for Chem 20. This is the final lesson of the bonding unit, looking at relating all the different structures of matter that we talked about with some of the different properties of matter that we know. So first of all, let's start with states of matter. So first of all, the state of a substance depends on the strength of attractive forces between its particles. So when we have solids, they're being held the closest and they're moving a little bit, but not very much. They must have the greatest force of attraction. Liquids are still attracted, but they're more free to move around, whereas gases have very few interactions between them at all. They're free to move around and they're not even really interacting. Solids could be crystal or amorphous, so meaning they have a 3D lattice structure or no orderly arrangement. Molecular compounds are usually not solid unless they're composed of a very large molecule, such as a polymer. A polymer is a repeating unit like DNA that repeats over and over. That, again, because it's so big, it has so much surface area, this is what makes it solid. For melting and boiling points, we talked about this already in the last unit, but again, the last lesson. Again, just to review, the strength of attraction within or between molecules is what determines their boiling point. When we melt or boil or go through some phase change with a metal, you do have to break the metal bond. Remember, the metal bond was the cations with a sea of delocalized electrons around it. You have to break that whole structure down in order to go through a phase change. So generally, metals have a very high boiling point. Ionic compounds, as we know, are all solid, so they must also have a fairly high melting and boiling point. And it's because the crystal lattice structure that ionic compounds take on do need to be broken. The ionic bonds themselves need to be broken. However, in a molecular compounds like we talked about, only the intermolecular forces are broken. The covalent bonds do not break. When I have water and I boil it, it's still water. It's still H2O. It's not hydrogen gas and oxygen gas. It still is the whole molecule. It's just the molecules have spread apart. So the covalent bonds are intact. It's just the intermolecular forces, the London dispersion, dipole-dipole, and hydrogen bonds that break. And as we know, these are the weakest forces. So this is why molecular compounds have the lowest boiling points. But you can order a group of molecular compounds again based on the number of forces it has. The more forces it has, the higher the boiling point. What are some other properties, some mechanical properties of solid or liquids? So this is when we talk about their malleability and their ductility, their flexibility, in other words. So as we know, metals, they have the ability to move. They can bend, they can be shaped easily. That's because of their delocalized electrons. So you can freely kind of move the atoms around and they just slide around with that electron cloud, sea of electrons sliding with it, and it keeps its structure. So that's what makes them malleable and ductile. So they have what's called non-directional bonds. But if they have directional bonds, which are what ionic compounds have, they're brittle and hard. Because if you try to move them, you're going to, before you had positive and negative ions beside each other, you might put two positives and two negatives beside each other, which will repel. So then they fall apart. Are liquids or molecular compounds? Molecular compounds do have some transitional motion. They can flow around. But again, the amount of movement they have, whether they're like really viscous and they're thick or if they're really easy to move, depends on, again, the number of intermolecular forces they have. So their surface tension, their viscosity, how their volumes combine when they mix. They might not combine equally because they can fit in the inner spaces between them. Capillary action, the crawling up of molecules on a piece of paper, for example, or along the glass of a beaker, because it's attracted to the walls of the beaker. So the more forces of attraction they have, the stronger these things are, the stronger the surface tension, viscosity, and the capillary action. Also of important note is that you may have heard before the saying like dissolves like. So if you want to find if something is soluble in something else, and there will be a question like that on your test, you're asked if something is soluble in water. We know that water, which is H2O, oops, sorry, my pen just turned the page. If we have H2O, it is both polar, so it has London dispersion, dipole-dipole, and it has hydrogen bonding because H is bonded to O. So if we want to find if something is soluble in water, it has to have those same forces. It also has to have London dispersion, dipole-dipole, and hydrogen bonding. The more forces that are the same, the more soluble or the more miscible it will be. If they have different forces, they will be insoluble with each other. Conductivity, whether or not the electrons are free to flow, but it could also be whether or not there are ions free to flow. So it doesn't just have to be electrons. It could also be positively charged ions. Their flow also conducts electricity. So metals we know conduct well because those electrons are free to move. They're the sea of delocalized electrons. So those electrons can move, carrying current with them. Ionic compounds, if they're in their solid phase, they will not conduct electricity because the ions are all held together in the crystal lattice structure. But when you melt or dissolve them, so you make them liquid or aqueous, they will conduct electricity because the ions are able to move. So again, the positive and negative ions can flow around, and that's what carries an electrical current, allowing for electricity to be conducted. There is a lab that we're going to do in the solutions unit, and we're going to look at ionic compounds versus molecular compounds and their conductivity, and it asks you why ionic compounds, when they're dissolved in water, conduct electricity, and you are going to say it's because the ions are able to move, and that carries an electrical current. Molecular compounds, on the other hand, do not. They do not form ions when they're in solution. If I have a molecular compound, let's say I have CO2 gas. When I dissolve it in water, it's still CO2. It doesn't break into carbon and oxygen ions. It's not made of ions, right? The atoms are sharing electrons. They're not formed by a division of electrons like ionic compounds are. Right? These are all being held together. So whether they're in water or not, they're the same structure. They're not free ions like ionic compounds, right? Are free ions, sodium chloride. The ions, I guess I should put the negative outside. Sorry, let me redo that. So the chlorine has the full 8 electrons, and it's -1 charge. When they're held together in the crystal lattice structure, they can't conduct, but when you break the crystal lattice structure apart by melting them or liquefying them, they are free to move. And because they have an ion charge, they can conduct. Okay? Molecular compounds do not have an ion charge. Even if they're polar, they still don't have a full charge. So they do not conduct whether they're dissolved in water or not. They never conduct. Okay? And that's it. So we're done the unit. You'll need to hand in your workbook and vocab the day of your unit test. There is a review at the end of the workbook that you now need to work on. And thank you for watching this video.